Hello and welcome to all students. This is SY BSc class semester 3rd, paper 1, calculus 4, unit number 1, Riemann integration, and today we are going to see theorems on Riemann integration. If f be a bounded function defined on bounded and closed interval AB, if closed interval AB, function f is Riemann integrable on closed interval AB if for each epsilon greater than 0 there exists a subdivision sigma of closed interval AB such that UF sigma is strictly less than LF sigma plus epsilon. Okay. In the properties of upper sum and lower sum, we have seen that lower sum is always less than or equal to upper sum, but if for epsilon greater than 0 there exists some subdivision sigma which gives us UF sigma is strictly less than LF sigma plus epsilon if f is Riemann integrable. So this is if and only if. Therefore we prove this theorem into two parts. Okay, so let us start now. In the first part, okay, so we write here part number 1. Part first. Okay, so in the part first, so we take given thing, let, or we write here if epsilon is greater than 0, it is given there exists a subdivision sigma of closed interval a comma b such that upper sum of function f with respect to subdivision sigma is strictly less than lower sum of function f with respect to subdivision sigma plus epsilon. Okay, so let us call it is equation number 1, which we will be used in further. Okay, we write our claim here. What is our claim? What we have to prove? We will write here. Claim is to show that function f is Riemann integrable on closed interval a comma b. So this is our claim. Okay, so let us start to write the proof now. Okay, we know that integration over a to b means upper integration of function f is equal to greatest lower bound of all upper sums of function f over subdivision sigma therefore upper sum upper integral of function f is always less than or equal to upper integral or upper sum of function f over the subdivision sigma. This is our second equation. Now similarly we know that Similarly, we know that the lower integral integration a bar a dash b of function f is equal to, it is least upper bound of all lower sums of function f or her subdivision sigma. Therefore, we can write, as it is a least upper bound, the value of this lower integral is always greater than or equal to lower sum of function f with respect to subdivision sigma. Okay, so from 1, 2 and 3, from 1, 2 and 3, we can write integration means upper integral of function f is strictly less than lower integral of function f plus epsilon. Okay, since epsilon is arbitrary, since epsilon is arbitrary, we have integration or upper integral of function f is strictly less than integration or lower integral of function f. Okay, this is okay, but we know that, but by the properties of lower and upper integral, by property of upper and by property of upper and lower integration, we have integration or lower integration of function f is less than or equal to upper integration of function f, and from these two things we can write upper integral and lower integral are same. From these two things we can write integration or lower integration of function f is equal to upper integration of function f, and from this equality we can say that f is Riemann integrable function on closed interval ab. So this is the proof of part 1. Now we prove the second part 2. Part second. Okay, in the second part we take, in the second part we write in part 2 we write the given thing, given that f is Riemann integrable on closed interval ab. Okay, that is, this implies that in lower integration of function f is equal to upper integration of function f. Okay, now what is our claim is to show that upper sum of function f corresponding to subdivision sigma is less than lower sum of function f corresponding to subdivision sigma plus epsilon for some subdivision of closed interval AB. Okay, so now we take up to here. From given integration over a to b of function f is equal to greatest lower bound of u f sigma over subdivision sigma is equal to integration or lower integration or lower integral of function f and is equal to least upper bound of all lower sums of function f over subdivision tau. So this is we have from given. Now let we write here. Now let epsilon greater than 0. Let epsilon greater than 0 be given. Then from definition of least upper bound we have for subdivision sigma, here we write, then from definition of greatest lower bound we have for subdivision sigma for subdivision sigma for subdivision sigma integration or upper integral of function f plus epsilon upon 2 is strictly greater than upper sum of function f. Okay, similarly we may choose a subdivision tau such that, let's call it as equation 1. Similarly we may choose subdivision tau such that lower integration of function f minus epsilon by 2 is strictly less than lower sums of function f corresponding to subdivision tau. Okay, that is lower integral of function f is strictly less than lower sum of function f corresponding to subdivision tau plus epsilon by 2. Okay, that is we can write lower sum of function f corresponding to subdivision tau plus epsilon by 2 is strictly greater than upper sum of function f corresponding to subdivision tau minus epsilon by 2. Okay, for any subdivision tau, therefore for any subdivision sigma, this implies uf sigma is strictly less than lf sigma plus epsilon, and this is the end of our proof, and this is the end of this lecture, and thank you for paying attention.